Now, we're going to talk about the magnetic fields of the planets and the stars. And this comes at us from work that my old friend James Van Allen did. He was a personal friend of mine. He wanted me to join him up in Iowa, but the trouble was in the winter it's like the Arctic, and in the summer I'm allergic to everything that grows there, so I didn't go. But it was a nice invitation. Van Allen unfortunately died of a heart attack a couple of years back. So this is the Van Allen hypothesis, the origin of the magnetic fields of the planets and stars, by myself. And Van Allen has experimentally observed that the magnetic fields of the angular magnetic, wait, I have to rotate so I can read my own slide. Van Allen has observed that the magnetic moments of the planets and the stars are proportional to their angular momentum over some 12 orders of magnitude. And he gave me the experimental results. Next slide. This graph is purely empirical. It is regarded with disdain by theorists of the planetary magnetism, Van Allen. So the people just laughed at him. In this presentation, I develop a model that both predicts the proportionality between the magnetic moment and angular momentum, and also fits the experimental results with no adjustable parameters. And this would be very nice. It would be worth a very large prize, except it wasn't done at Harvard. And so that's the basic problem. I did my undergraduates at Harvard, and it's a fun being at Harvard. The old joke is the shortest way to Moscow is to go to Harvard and turn left. But only one of my college professors was a card-carrying communist. I knew that because he told me. That's a fact. Next slide. This is the graph that Van Allen made, and we go from all the way up from the sun down to Pluto, and each one of these notches is a factor of 10. So this line is over 12 factors of 10. Now, it's an interesting graph, but this is an empirical result, and this is what he gave me. And here's pulsars, for example. And he had another graph that had some more stuff on it. It also fell on this line. So where does this line come from? This is an interesting problem. Next slide, please. Okay. Now this is the conventional model of the Earth's magnetic field. What it is there was a famous theoretician named Cowling who proved that you cannot generate magnetic fields by magma flow in a symmetrical situation. There is no magnetic field in the core of the planet due to iron, even though the core is iron, because the core is molten. And it's above the Curie temperature. Madame Curie and her husband discovered the Curie temperature, and that's a temperature above which metals become non-magnetic. And you can make actually a little motor. I was going to bring one in, but it had a fire on it, and I decided that I didn't want to bring a fire into a theater. So we have enough problems. So this is a very complicated model. It has all sorts of spiral convections. This is the liquid core. The center of the planet is apparently solid iron, but it's too hot to be magnetic. We know the core is liquid because earthquake waves propagate only in pressure waves that oscillate back and forth in the direction of motion, and shear waves. But the shear waves do not go through the liquid, so you only get a pressure wave across. So that's how we know the core of the planet is liquid. Now this model predicts you can get a magnetic field. It doesn't predict the magnitude, and that's an interesting problem. Now, the planet's core does probably modify the magnetic field. The core, liquid core, shows up in things like the magnetic poles migrate. They move over the surface, and they've migrated hundreds of miles since they were first discovered. But that's a secondary effect in my knowledge. So let's go ahead with the next slide. What is significant about October 31st, 1992? Anybody know? Huh? No. The basic thing is That previous slide was gospel, and it cannot be challenged. It's the present magnetic field model of the Earth. And this date, October 31st, 1992, was the year in which Pope John Paul II officially declared that Galileo was correct. The Earth does go around the sun and not the other way. It only took
until 1997 that the church absolved it.
That's true, but actually there was another output in the year 2000. But this is when the Pope actually said, yeah, it was only a little over 400 years. So anyhow, so this is gospel in astronomy. There are gospel truths in astronomy. And one of them is about the Earth going around the sun. All right, next slide, please. The model is based on the fact that each rotating planet and star is immersed in a non-rotating conducting plasma cloud, which constitutes a Faraday electrical generator. The Faraday generator is assumed to be the primary source of the magnetic field, in contrast to present models that assume that the flow of magma in the planet's cores is responsible. So that's the difference. Of course, the core does store magnetic field, but the magnetic field decays fairly rapidly compared to the life of the planet. And so it modifies the exterior field, but it does not generate it in this model. Next slide. Hello, next slide. Okay. This is a Faraday disk generator. Michael Faraday essentially invented the first electrical generator. And you take a rotating disk and have it present in a magnetic field, and it generates an electrical voltage. The voltage is radial. That's better. It comes from the outer edge and goes back to the axle. This is the Faraday disk generator. We'll show you a couple of these disk generators. Am I coming in really clear? Well, that's amazing. Look at that. We have some miracles available. All right. Let's take a look at the next slide. Okay, thank you. This is a model of a Faraday disk generator. This is probably Faraday's original model. You rotate the disk, and here is the magnetic field. It's a U magnet, and the current flows radially to this sliding brush and comes around in the external circuit to this input wire. And actually, you can drive the disk with eddy currents. You don't have to have sliding contacts. And I figured out a way of driving liquid salt water with a magnetic field to make a submarine drive that had no noise. There was no mechanical moving parts. And I got a patent on it. And two branches of the Navy killed each other over it, and nothing ever happened, which is what normally happens in the military. As you probably know, in the Civil War, the reloading rifle was available to the Union troops. And how many Union soldiers had them? Plenty of them, but they had to buy them with their own money.
They gave them to the Indians.
Beg pardon?
They gave them to the Indians.
Later, that's right. But that was the Winchester, lever-loading Winchester. All right, let's go to the next slide. This is an actual model of a giant Faraday generator. It was at the Australian National University in Canberra, and this thing is brought up to high speed. This is just pieces out in the lawn, of course. Then you short circuit the outer conductor, and you get a tremendous pulse of current. And they were using this for fusion experiments and also for rail guns. As you know, electromagnetic rail guns are being investigated by the military. The standard rifle bullet cannot go any faster than the gases propelling it. So the standard rifle bullet can only go maybe twice the speed of sound. It goes faster than regular sound because the gases are hot. But electromagnetic guns, the limit is the speed of light, and that's pretty fast. Next slide. Hello, next slide. This is my model of the Faraday generator, but it has a new feature. Here is a rotating planet, and it generates a radial current. Now, how does the current complete the circuit and make more magnetic field? Well, we have a plasma stream here, and it takes off at the equator and ends up at the pole. Now at the equator, the plasma just goes over the equator, and we'll talk more about that later. But at the pole, it dives into the planet. So it's tied to the planet, and as the planet rotates, this line bends. And if you play with the right-hand rule, you discover that this generates a magnetic field which emphasizes or enhances the original magnetic field. So that's the model, that's my contribution here. Now, I published a paper before on this, but I didn't have the model. This just came as a result of your invitation to this talk. So I appreciate your invitation. Next slide. Here are pictures of actual plasma streams on magnetic fields, and the plasma is moving and dragging the magnetic field along with it. And these are prominences on the sun. The Earth would be a little speck in the middle of here. So here's an actual example of these magnetic lines carrying current, which I theoretically predicted in the previous slide. So it does look feasible. So now let's make some mathematics. Next slide. Here's the model. Instead of making a sphere, I make a planet as a cylinder. And the reason for this is based on Fermi's work. Yeah, Enrico Fermi, he used to do things like, well, we're going to describe what goes on in a nucleus. Now let's take a cube. And you get the results within 20%.
Yeah, he did the same thing with cows.
Yeah, well, it's a lot easier to do that. And you get the result pretty well. So the planet is 2 radius long and 2 radiuses in diameter, and it rotates. All right, now let's put some math in. Next slide. Well, here's the magnetic field. This is what they call an operator, and for those not in the know, it really means that the magnetic field is divided by a number, and it's equal to mu naught, which is a constant because the current here and the magnetic field are measured separately, and we have to put this constant in to make it come out right. So that's the basic field. The current generates a Curie magnetic field. What is the constant to divide this? Well, the logical constant is the radius of the planet. So magnetic field divided by the radius is equal to mu naught times the current density. Okay, next slide. Okay, next slide. Well, the current is generated by the plasma rotation. J is equal to the conductivity times the velocity of the equator times the magnetic field, and it's equal to the current, conductivity times the angular velocity times the radius times the magnetic field. So this generates the current, and the current generates the magnetic field. So next slide. Well, you discover that this gives an ambiguous situation. The magnetic field over the radius is equal to this constant, the conductivity, the angular velocity, the radius, and the magnetic field. So the field goes up, the field goes up, and it keeps getting higher and higher. Now, this was actually discovered, as I remember, by the German scientist Siemens. He made the first practical electric generator. And he took the output energy and put it back into the magnetic field, and the thing caught fire. And he said, hooray, it works. But we have to figure out how this is limited. And we don't want something to catch fire, especially the Earth. Next slide. The solution is to use Bohm conduction across the magnetic field. Now, David Bohm was a very interesting scientist who worked at Oak Ridge National Laboratory. And he discovered what they call Bohm diffusion. And Bohm diffusion was a funny thing. You made a fusion machine, you know, you trap the plasma in a magnetic field, and it goes pouring across the magnetic field. And it went by a number called Bohm diffusion. Bohm never said where his mathematics came from. And he finally ended up dying in England. And he made one major scientific achievement that was very great. If you ever play with magnetic fields, there's something called a vector A. And you take the vector A and play with it, and you get the magnetic field. And Bohm proved that the vector A had a physical significance. And so he did a great deal of success with that. But the thing is about the Bohm diffusion is it's not really diffusion. That's why people couldn't figure it out. What it is convection. And what happens is you have a plasma column in a fusion machine, and suppose one species, say the electrons, gets out faster than the ions. What happens is you get a radial electric field and the column starts spinning. And what happens is the outer column is touching the wall, so it doesn't spin. So there's shear in the column. And in an extremely short time, it breaks up into little spinning eddies that actually carry the plasma to the wall very rapidly. If you can get rid of this electric field, Bohm diffusion goes away. So what it is here the current is equal to the conductivity times the electric field. And it's equal to E, the electric charge, N, the number of free electrons, V, the drift velocity. And in Bohm diffusion, the drift velocity is given by E over B. Now, normally that would be moving at right angles to the electric field, so it wouldn't be conductivity. But I showed at Oak Ridge, a long time at ORION, first experimentally and then theoretically, that this immediately goes into eddies and carries the electrons across the magnetic field. So what happens is this B cancels out another B and the ambiguity goes away. And that's very nice. And so I found this. Of course, nobody really cares. One of my engineers came in one day after giving me a hard time, and he said, you know, your theory is right, and the Russians did it first. So that's my life at Oak Ridge National Lab.
You are Russian.
Да, конечно, я говорю по-русски. I haven't commented about Russia. One of the things that I did at Oak Ridge, they came and asked me, can you figure out why the calutrons, which separate U-235 from U-238, why you can't get a very high current? Something goes wrong. And it's much lower than the actual current produced, but something goes wrong, the separation stops. So I did a lot of theory and came out with a result. I figured out what it did and wrote a report. And I asked them, what did you do with my report? What impact did it have on making atomic bombs? And they said, oh, that was a wonderful report. It was so clear, so wonderful. We sent it to the Soviet Union on the exchange of information. It actually happened. So I published it, I got permission. What could they say? You know? But anyhow, it was a very interesting instabilities thing. The plasma machines that separate uranium are like the American society, totally unstable, but the instability is below a certain critical threshold. That was the thing. All right, let's go ahead. Next slide. The net result for the magnetic field is as follows. The magnetic field is no longer ambiguous. It's given by mu. It's supposed to be mu naught, but you know that, and I know that, but my computer doesn't. E n sub e, the electron density, omega r squared. So this is the net result for the magnetic field. Next slide. The magnetic moment m for a cylindrical model of radius r and depth 2r, which is the one I showed you before, is m is equal to 2 pi mu naught, the zero came back, E n omega r to the fifth. So that's the magnetic moment m. Next slide. Here's the model again, just to remind you what it is. Magnetic field is coming out here. Current is coming from the outer surface and flowing in here. Next slide. The angular momentum L of a cylinder of radius r and depth 2r is L pi m omega r to the fifth. So let's divide the two. Next slide. Well, you discover that the result between magnetic moment m and angular momentum L, m over L, is equal to 2 mu naught E n sub e over m. All the other numbers cancel out. Now, mu naught is a constant. It's a constant of nature because people measured magnetic fields and electric currents in different units. E is the charge of electron. You can't change that. N sub e is the electron density. So what electron density should we use? It's an interesting question. Well, what I found is in outer space, away from the planets, there's plasma. And there is an n sub e in outer space. It's probably too low for the model, but we'll use that as a first approximation. M is the average mass density of planets and stars, and they're all about the same. They're light elements like lithium, hydrogen, helium, and stuff like that. The only true free variables are the plasma electron density and the average planet density, and we can approximate that. So let's see what we get. Next slide. Here's my line.
Wow.
And actually, I've made a correction that moves it over. There are no adjustable parameters. It's low because of the fact that I used a low value for the electron density. And a couple of the planets are off scale down below. And one of my students, a fellow named Burchett, pointed out that this model is just the maximum value. It can be 0 or reverse. There's no time behavior in the model. This is just the maximum magnetic field. So these can be easily explained as going through the transition. As you know, the Earth's magnetic field is reducing, and the world will come to an end very shortly when it goes to 0, of course. You'll notice that there are no planets or stars above the line. They're only below. And I have to put in the time dependency on that. So this is the final result. It looks pretty good. I've actually published it, and there has been no reaction whatsoever from the Astronomical Society. It's been published for about 10 years. But because it violates the gospel truth that the magnetic fields of planets and stars come from the cores and not from the interplanetary system. And I think that concludes my slides. I have a poorer copy of this one, but anyhow. So I actually, yeah, go ahead. Question.
Yeah, what is the physical significance of the magnetic moment? Is it the same as the strength of the magnetic field?
Well, the magnetic moment is the energy stored in the rotating plasma, the mechanical energy stored in the rotating plasma. That's not the plasma, the star. It's the rotating energy stored in the angular momentum. It's essentially how many watt hours do we have in the rotation of the Earth. That's significant. It tells us how long it'll take the Earth to go to 0 with the tidal drag, the Earth's rotation. You have another question? Yeah.
I have a question.
Okay.
To put this in practical terms, if you compare the magnetic field of Mars, for instance, and the magnetic field of the Earth, does it comply with the curve you just showed?
Oh, yeah, it's on that line.
Straight line curve?
Yeah, it's on the line. They're all on the line.
Whether that arrow indicated...
Well, they indicate that some are below, and that is consistent with the model because the model is just the maximum magnetic field. But if we go back a slide, can we go back a slide?
Yeah, he's rebooting the computer. I think it crashed.
We can go back in time a little bit.
Is this, now, Mars has a lower density and has lost most of its magnetic field?
Well, let's take a look at that slide. It could be that, or it could be just going through a reversal. What you have to do is look at the planets' reversals of the magnetic field. For example, the Earth has gone to 0 magnetic field numerous times in the past and gone from the North Pole to the south and the south to the north.
Why?
Well, that's because the model is oscillatory model. It actually has no steady state. It goes from one side to the other. That's what my model would say. But experimentally, what you do is you look at various strata, and as strata are deposited, magnetic materials are aligned to the magnetic field. And you see the magnetic field in one direction, and suddenly it reverses 180 degrees. It's a geological proof. It's not something we speculate on. Any other comments, jokes, or sarcastic remarks? Yeah, way in the back.
Did that occur when as the rock cooled during one polarity or the other? When the rock got below its what do you call it, Curie point?
Well, it could be somewhere like that. A lot of it's in sedimentary deposits where you have magnetic materials. I'm certainly not an expert on the geology of the Earth's magnetic field changes. But it's certainly the magnetic field of the Earth is going down a lot. And right now it's decreasing, and it should be, I think, zero in about 100 years. And then it probably will reverse. Any other questions?
Yes, sir. That's very interesting. So what you have is an empirical model that seems to give the amplitude, the maximum amplitude of the field based on the scale according to the momentum.
This one, yeah.
This one. It seems like if it has validity, even though we can't derive it,
What's that?
even if this has empirical validity, it would predict, as well as some of the other models, that there's a fluctuation there.
Well, we have to put the fluctuations into it.
Right.
But these are the maximum, and that is not an empirical thing. That's a theoretical model with no adjustable parameters.
Right.
Let's see if we can get those slides back. Can we get some of the graphs back?
Has it been applied to moons? There's some large moons of Jupiter, and our own moon is large compared to the planet.
Well, Van Allen didn't have that on the graphs. It may very well be that the moons of Jupiter follow the same model. But
Our moon doesn't, I believe. I believe our moon is
beg pardon?
I believe our moon does not follow that model.
It follows this model. The moon is down. In other words, the field is low, but that would correspond to going through a field reversal. None of the moons are up here. They're all down here. Let's see. The question about Mars. Mars is essentially on the line, though a little bit low. So Mars does fit this model.
Is the value that you have here for Mars the value that Mars would have had before it lost its magnetic field?
No, that's the present value.
The present value.
Yeah, see, it's way down on this curve.
Yeah.
Yeah.
This model says that you have this rotating object inside a plasma.
Yeah.
Now, where is the origin of the plasma, then the solar wind, and where do these?
Well, what I used is if you get away from the solar wind, the interstellar space has a plasma density. It's a constant throughout interstellar space. Interstellar space is not a vacuum. And if I remember correctly, the value is about 1 electron per cubic centimeter. I'm going back on them all. So interstellar space is not empty. It's full of plasma all the way out, as far as you can see. And that may have some interesting results on the propagation of electromagnetic waves in space. Now, although I think nobody worries about it. I use the value of interstellar plasma density as published by NRL. The Naval Research Lab has a little notebook and has all the constants of nature, and they had the density of interstellar plasma there. If you say that the plasma should be higher because of the solar wind and stuff, this line should move up.
Have you tried to do that?
No, haven't done that.
Let's do it.
Well, we could. Why not?
Now,
But we could also probably put in the time behavior, because the magnetic field in the core of the Earth is due to eddy currents, and it has a certain decay time. So it's stored there. Yes, sir.
If you had that generator that you showed earlier, and that was generating, the polarity wouldn't reverse on that.
If it goes to zero, it could.
Well, would it have to stop spinning?
No, what happens is the magnetic fields can start decaying, and then the field goes down, and it becomes unstable. It goes through zero and goes back and forth again.
It could start decaying even when it's spinning?
Yeah, sure
What causes
could.
that?
Beg pardon?
What would cause that?
Well, the model is basically an oscillatory model. It could be that the magnetic field in the core hits a certain value and it starts absorbing energy. I have not pushed that. Good questions. The model could easily be adjusted, and in 400 years following the Galileo, we might have it recognized.
It may not be too different from the Rayleigh instability.
Rayleigh-Taylor instability, well, it might not be, but it's an interesting
The
question.
density differences and their... Now, I got a question though. How does Alfvén figure into this? Because I hear of a conservation law that we normally don't teach our students, but should, that the magnetic field lines are frozen in the plasma, and therefore the line density is conserved. So if you take a large object like our sun, and when it becomes a white dwarf, then the magnetic field lines the number are maintained, so the magnetic field of the white dwarf dramatically increases.
Yeah, I hope I'm not around when that happens.
Yeah, 5 billion years or so.
Igor, does the left-hand rule in electronics have anything to do with this at all?
Well, yeah, the right-hand rule. That gives you the way the field curves, as I showed you, generates a solenoidal magnet out of plasma lines that reinforces the original field. Yeah, right-hand rule. Fingers go in the direction of current, which of course is positive ions.
And it's right-hand rule, not left-hand rule?
If you use the positive current, if you go electrons, which they screwed up with in the old days.
Yeah,
But
right.
current flow in electrical systems is positive charge. That's a historical accident. Again, something that will be corrected in another 400 years.
So it's a right-hand rule, but it's the same principle. as the
Same
left-hand
principle,
rule.
yeah.
It's just misstated.
Yeah, well, it's not misstated, it's right.
I mean, it was misstated.
Yeah,
Thank you.
it's right by definition. Any other questions, jokes or sarcastic
The
remarks?
right-hand rule becomes the left-hand rule.
Well, if you follow electrons.
I mean, never mind, I'm getting y'all confused. and I
Yeah.
don't do that.
And he was going to answer my question on alphane, where you asked yours.
Well, it's an interesting question. Alphane's calculation is for a perfect plasma. If you have finite conductivity, it's not true. Well, the two important things out of this talk are the line here and the fact that we have Bohm conduction. And that's an interesting problem. But interestingly enough, David Bohm did Bohm diffusion while working on the uranium isotope separators at Oak Ridge National Lab.
That's really a stimulating talk. I think all of us are thinking.
Well, we could do
why don't
something.
we just add what's missing and have some justice in less than 400 years?
Well, we have to wait 400 years. It has to age properly.
Yeah, it's religious
Can we get
questions.
copies of this?
Okay, I get to do something.
Yeah, he has some copies. They want copies.
Copies, yeah, I have some.
Copies of the lecture.
I don't have copies of the lecture, and of course it's incomplete because some of the things had to be done, but the original paper I have copies of, but I don't have a large number. So we can raffle them off. Oh, what's
This
that?
does not get raffled. This is a treasured Orion cup. It's not yet 400 years old, but eventually.
Well,
it will be.
that's
And it
the,
goes to our esteemed speaker.
well, thank you very much.
You're welcome.
That's actually the national symbol of Korea, isn't it?